Electricity market integration. So we're going to talk about intermittent renewable generation. We've talked about this a bit, but we're going to expand on it. Market integration and Davis and Hausman paper. There's a lot of excitement about renewable generation. This little figure shows capacity in gigawatts for wind from 2006 to 2016. You can see it's increased substantially. For solar, also from 2006 to 2016, capacity has increased substantially. There's dramatic growth in the share of electricity from renewable sources. So what matters is not the actual capacity increase, but the share of renewables on the grid. And we'll talk about why that matters in a moment. It's driven by wind and solar. Hydro and nuclear are relatively unchanged. Growth reflects falling costs for both wind and solar. We saw that in the levelized cost of energy analysis a few lectures ago. The problem, though, is renewable generation is intermittent. This is the main problem with renewables. A challenge is that wind and solar generators are intermittent. There's less control over when they produce than fossil fuel generators. So even if a wind farm is rated at 100 megawatt capacity, it may only produce a fraction of that capacity at any given time. And it may, its capacity utilization or its generation may fluctuate on an hourly basis. Intermittency is problematic. Supply must equal demand at all times on the grid because there's no storage. When renewables turn off, other generators must turn on. So if supply must equal demand and the wind stops blowing, causing wind power to decline, other generators must meet that the additional demand that was previously met by the wind power. It's not a big problem when renewables are only a small fraction of total generation, right? So if only 1% of your total generation is coming from wind power and that wind power shuts off, then you've only lost 1% of your total generation. It becomes a much larger problem when renewables make up a more substantial fraction of generation. For example, in 2017, wind power provided 37% of Iowa's electricity. A very quick 37% decline in electricity production is going to be a big problem for a grid. Potential solutions include low-cost electricity storage. We have two types right now that aren't really low cost, but they're getting there. There's battery storage and then pumped water storage. So pumped water storage is when you take electricity and you pump water up a hill, you put it in a reservoir, and then when you need it, you release it, and it comes. It's basically just creating your own little hydropower station. Why would this solve the problem? Well, the batteries can be charged during low demand times, and then during peak demand times, or whenever they're at any point really, when wind or solar is providing some fraction of the power, then when the wind and solar go offline, you can replace it with the electricity stored in the batteries. You can penalize intermittent generation. You can essentially tax it. That's another solution. You can increase the size of electricity markets. So if electricity flows freely from across the whole eastern interconnection, days when it's not windy in Wisconsin can be offset by windy days in Florida. So you can actually get wind power from Florida all the way up to Wisconsin because the electricity is traveling basically the speed of light. You can also introduce real-time pricing. If people respond to quick changes in the wholesale price, then they can cut their consumption when prices peak because wind power has declined. So this is the state of renewables on the electricity grid today. The electricity grid is dynamic. It's changing all the time, and some combination of these solutions is going to be needed in order to make renewables more viable. There's a lot of states that have vowed to go 100% renewable by some date, maybe 2035 or 2050. And to do that, they're going to have to do some combination of these things, because it won't be possible to meet demand with with 100% intermittent supply. So let's turn to market integration, and to do that, we're going to look at a case study, the one that was evaluated by Davis and Hausman. So they looked at the closure of a nuclear power plant in 2012. It was a large power plant, 2 gigawatts capacity, 8% of California production, and it suddenly closed due to cracks in the boiler. The fixed costs of repairing the cracks plus ongoing operating costs were too high relative to the expected prices in the future. And so this power plant, this Songs nuclear power plant, the ownership opted not to spend an extra $340 million to keep the plant open. Another factor was the low gas prices leading to low electricity prices. So this is kind of what was happening to coal plants, or what is happening to coal plants. The natural gas prices are coming down, causing the nuclear and coal plants to shut down. Here's a graph of the natural gas prices and peak wholesale electricity prices. So the highest prices for different times of the year or different years. The peak electricity prices are the little circles. You can see they've been coming down over time, and that's primarily due to the natural gas prices. So natural gas is the peaking supply. They're the marginal producer. They're the ones furthest out on the supply curve, the dispatch curve, and they're setting the wholesale prices. The brown or orange, that's the nuclear power plant operating expenses. You can see towards the end of this graph, the peak wholesale prices are becoming are lower sometimes than the nuclear power plant operating costs. So they weren't breaking even; they were losing money. So the Songs closure, it avoided $350 million in fixed costs and additional operating costs. It eliminated nuclear meltdown risks. It increased generation costs at natural gas units by about $350 million. Why did it do that? Well, if you take out 2 gigawatts of production from nuclear, it has to be, that lost supply has to be met from somewhere, and in California it was met by additional natural gas production, which increased natural gas production costs by $350 million. $40 million of that was due to transmission constraints, and that has to do with where those plants are located relative to population centers or demand hubs. It increased, so sort of like the locational marginal prices we saw in the previous lecture. It increased carbon emissions by 9 million tons, so going from nuclear, which has 0 carbon emissions, to natural gas, which was equivalent to about $450 million in emissions damages, and it's also equivalent to putting 2 million additional cars on the road, and it resulted in large increases in wholesale electricity prices. And this paper kind of asks, why did the wholesale electricity prices go up? The Songs was located between Los Angeles and San Diego here, right between 2 population centers where demand is really high. So this means that the Songs location was optimal for electricity generation. Southern California had more demand relative to inexpensive generation capacity than Northern California. Before the Songs closure, electricity flowed from north to south, but prices were equalized. So basically, there was high demand in the south and a lot of excess supply in the north, and so that excess supply in the north was then transmitted down to the south, but there was enough generation in the south to combined with the north supply to meet demand. But after the Songs closure, the lines became congested at peak hours because there was insufficient supply in the south to meet the peak demand in the south, and so they were trying to get excess supply in the north to come down to meet the excess demand in the south, but there was insufficient capacity on the transmission lines to get that power flowing from the north to the south during the peak times. There was also congestion within the south. Songs located was located in a swing region between LA and San Diego, and Davis and Hausman find transmission constraints cause Song's closure to be about $40 million more expensive than they would have been without transmission constraints. And then finally, market power. There were two generators owned by the same firm, and they increased generation by less than expected after the closure. So after the closure, the demand needed to be met by something. And if you are going to be the marginal producer, you're the one, you're way out on the right-hand side of the dispatch curve, the supply curve. You can increase prices by withholding some capacity or bidding higher supply curves. These generators did that, and they were later found guilty of market manipulation in California and the Midwest, and they were forced to return $125 million in profits and pay $285 million in penalties. And the paper looks at generation costs, but suggests firms were also exercising market power. As a final note, this paper has a great figure with the aggregate supply curve. We've looked at sort of pretend ones, but this paper gives us the actual aggregate supply curve in the region. It's given it sort of like the step functions we've been dealing with, except this one is a little bit has a little more curvature to it, but it does have steps. So you can see at zero marginal cost, you have hydro and renewables, and then you have nuclear. And then you have natural gas in purple, the combined cycle natural gas, and then out to the right of that you have the more expensive peak load suppliers. And the histogram is total hourly generation, so it's basically a PDF of the hourly generation in the region.